All right, back into section 2.2, still talking about limits of a function. I'm just trying to break the videos up a little bit. So let's look at these two functions. F, 1 over x, sometimes they call this the reciprocal function. Then I've got g of x here is 1 over x squared. Okay, so I'm just going to kind of do a rough sketch of I'll start with f over here. Get my y-axis, my x-axis. All right, and you can plot some points with this. First of all, the domain of this function f is all real numbers except 0, right? Because we can't divide by 0, which means when x is 0, this function won't exist, which is on our y-axis. So this function has no y-intercept. And same for this function g, okay? So 0 is not in the domain of these functions. What that means is f of 0 does not exist. And also then when we come to g of 0 does not exist, right? Okay. If I plug in positive x values, positive over positive, we're going to get positive y values. You're probably familiar with this function. It looks something like this and something like this. Okay, so this piece of it for positive x values is completely up in our first quadrant. This piece completely down in our third quadrant. All right. My arrow hit the axis right there. This function never touches either axis, right? As you divide by, as x gets larger and larger, and you divide by larger and larger numbers, x is always positive, so 1 divided by a positive number is always going to give you a positive output. So it never actually hits 0, which means we'll never actually touch this line. Same business over here, and we already discussed it won't touch the y-axis. Okay, so I'll come back to g. Let me get rid of that. First of all, just to be clear, f of 0 does not exist. This function does not have a y-intercept, so f of 0 does not exist. Can I talk about the limit, though, as x approaches 0 of my function, right? And we saw in the previous video, the previous examples, that it's possible that the function value might not exist, but the limit still could, right? So let's just talk our way through this. As I approach 0 from the left, that means x value's right, I'm going this way, but that means I'm sort of riding the function. Where is this going? That's going down without bound, we might say. It's just going down and down and down and down and down. So let me alter this. As I approach 0 from the left, I could say that this limit is equal to negative infinity. All right. So limits can equal numbers, as we saw in the previous example. They can also equal infinity or negative infinity. A function value can't equal those things because that's not really a quantity, but the limit. Think about where, if you've seen Toy Story, right? Where is Buzz Lightyear going, right? He's going to infinity. And then he says beyond, but he's going to infinity. But does he ever get there? He's never like, I'm at infinity, right? So you can't get there, but you can trend down towards there. Same idea. As I go approach from the right, this function is rising towards positive infinity. So the limit as x approaches 0 from the right is equal to, some folks I've seen put a plus sign for positive, but you don't need one, is approaching positive infinity. Okay, there. So we've got the left-hand limit and the right-hand limit, but they don't agree. Negative infinity is not the same as positive infinity, so the overall limit does not exist. Okay, I won't write that. I could write that. Let's say limit, make sure I'm not in the glare of my screen, the limit as x approaches 0 in general, without the symbol, does not exist. Right, left, and remember the analogy. Your mom's going to the grocery store, your dad's going to the hardware store. Where are your parents going in general? You can't really answer that question. Okay, so that's this example. Let's look at let me just change it over here and look back to the example G. So what if I do x squared? All right, how's that going to change things here? So first of all, just for clarity, we'll still mention that g of 0 does not exist. So there's, again, still no y-intercept for this function. If I'm doing a rough sketch, I could probably leave this piece. X squared, I didn't really put any coordinates on here, so it doesn't really matter. The way that x squared works, though, is it kind of gets a little bit tighter. Well, it should pass around the same point, but kind of, that scale, look a little bit more like that. Hug the axes a little bit closer. Okay, so that piece is going to look very similar to our previous function. The difference is, though, now for negative x values, before it was just 1 over x, so those answers became negative. Now I'm taking these negative x values and squaring them. So we're going to get positive results. And so we actually get this symmetric, or you could argue even function that looks like this, right? So we say even, it's got that reflection across the y-axis right there. So there we go. So let me just maybe talk through these things, or talk through the left hand and the right hand. So the function doesn't exist at 0. It exists everywhere else, but g of 0 itself doesn't exist. As I approach from the left, it's climbing towards positive infinity. And as I approach from the right, it's also climbing towards positive infinity. So without writing the left-hand side, let me do this shorthand. Left-hand limit equals infinity. Right-hand limit equals infinity. Therefore, the limit in general as x approaches 0 of my function g, right? Don't want to say f anymore, g of x is equal to infinity. Okay, so kind of similar to the examples we saw in the previous video, except now we just have this thing. For both of these functions, actually, just to reiterate a few terms from pre-calculus. The graph doesn't exist at 0, but it's climbing towards, it's sort of approaching as you get closer and closer, looking like a vertical line. And sometimes you might see sort of a vertical line sketched in there. I'm using green as opposed to black, if that's clear. That is not part of the graph, but we can call it a vertical asymptote. Something like VA to mean a vertical asymptote is sort of a straight line that the graph is approaching. And the equation of that line would be, vertical lines would be x equals, and then whatever value that's passing through would be that. All right. And this function also has what's called a horizontal asymptote, which actually leads us to another type of a limit, perhaps. Okay, so we've got what's going on when x is, when it is 0, the function doesn't exist. When we're getting close to 0, which is what the limit notation means, the limit does exist. It's blowing up to infinity. What if we ask this question? What is the limit of this function g as x approaches? What if x approaches infinity, right? We saw that the y values can approach infinity. That was our limit last time. But what if the x value is approaching infinity? Can we ask ourselves that question? And this one we could actually sort of do analytically. If I plug in larger and larger x values, right? If x is approaching infinity, then we're going this way. It's getting larger and larger and larger. As you square those large numbers, they get even larger. And then you divide by those large numbers, and the output is really small numbers. And so here, you could argue that the height is approaching 0, right? And we're going to claim that this limit is equal to 0. All right. I believe it's section 2.4, I want to say, which is coming up in the future. There's one section that we're not going to cover in depth. I'll probably post a little video about it called the precise definition of a limit. Because actually, nothing we've done here is really that precise. We're just saying, oh, it gets close. You know, as x gets close to a value, y gets close, right? Well, there's not too much precision in that whole concept of getting close. So I'll probably revisit this example. We'll prove that this limit equals 0 down the line once we get to that topic, but kind of just based on the graph or based on your intuition of what's happening when we're dividing by these larger and larger values. Hopefully that's believable. All right. In my syllabus, I mentioned a graphing utility, Desmos. So I don't have a smartphone, so I use Desmos.com on the internet, but if you've got a phone, I think you can download an app. Go ahead and graph this thing and follow it, trace on your graph to the right. And at some point, you really won't even see the graph anymore. It's going to be so close to 0, it's going to look like it's laying on the line. However, we know it's not really on the line because, as we argued earlier, a positive divided by a positive can't all of a sudden equal 0, right? We're always going to be positive, which means above the line, the axis, but getting closer. So we've got this sort of horizontal asymptote, which I can write HA, and that's the horizontal line, y equals 0. All right, so the horizontal asymptote is the limit as x approaches infinity in this case. Alrighty, let me do one more, or a different type of function. I could record part 3, but this is a, maybe I will do that actually, because this is going to be what's called an oscillating function. So let me briefly pause.